Go ahead and get started today. Welcome to our 2023 day one of two capstone presentations for our space physics and astronomy graduates. We have 14 people graduating this semester that are giving capstone presentations. Let's preemptively give them a round of applause because they are doing great stuff. For our presentations today, each student is going to take about 5 minutes to give a quick whirlwind tour of their capstone and some of the stuff they're working on. The order of the presentations has been determined by the students choosing what day they wanted to present, if they sent me such a preference, and then telling me in what order they wanted to go right beforehand. So there's no preference given here whatsoever. But first today is Emilito Medina. He has been working with myself on a reduction pipeline for our spectrograph at the observatory, and he's going to tell us a little bit about that. So without further ado, Emilito, take it away.
All right, thank you, Dr. Richardson. Hello, everyone. Good 4 minutes afternoon. My name is Emilito Medina, and as Noel mentioned earlier, I am working with him on a data reduction pipeline for Embry-Riddle's Echelle spectrograph. So I'd like to start off by, talking about the project purpose. So this data pipeline is going to give us a more streamlined and standardized data processing method for our university's observatory spectrograph. It will refine the wavelength solution to a more accurate degree than by traditional methods, as I'll discuss near the end of my presentation. It will supplement observational techniques class and student research projects. And what could be done with this data pipeline is, given as an example, to your right, we actually have a spectra of the O-star binary CC Cassiopeia, which was taken in spring 2021. That's on the top. So in the middle, we actually have an eclipsing binary model for the flux, and on the bottom, it's for the radial velocities. Now to talk about the actual pipeline, there's 7 parts in total. I'm not going to go over part 7 because that's kind of trivial. What it does, it just reads in the right ascension and declination of a certain object and puts it into the headers of the images. So parts 1 through 6 are the main parts of the pipeline. Parts 1 through 3, we essentially take bias and flat images. Bias images are essentially like electrical noise coming from the camera, and flat images are sort of like the vignetting or the uneven field illumination from the dust or smudges. And we combine those with the images, subtract them out, and that just allows us to work with cleaner data and gets rid of these imperfections. Moving on to part 4 is actually tracing the flat. So we have a thorium-argon spectra, or an Echelle spectra, and what this part does is essentially counts the orders and the magnitudes, and as you can see on the right, it counts from 2 to 19. From extracting the flat, it'll just fit the background, traces and sums across the spectrum. And for part 6, the main part of the pipeline is our actual wavelength solution. So it's the main part of the code. It will automate the routine to extract and fit all the different wavelengths. And as I was saying before, finding wavelength solutions was historically done manually. And well, historically, one had to locate the coordinates of the emission lines, and then they had to refine the wavelength solution by comparing it to a reference wavelength list. And that's kind of tedious and hard to do. So why don't we just use code to automate everything? And unfortunately, we're not really done with this part yet. It's still being worked on. Yeah, me, Noel, and a couple other people are still working on a proper wavelength solution to get it working. So in conclusion, the end. Now I wrote the end because this marks the end of an era, my college career ending just next week because we're graduating. That's crazy. And with that being said, I would also like to thank the professors for teaching me a lot too, and I appreciate you guys' time for listening. So again, thank you, and here's my works cited.
Do we have questions today for Emilito? I will run around and take the mic to anyone that needs it.
Good.
Oh, we got one.
I'm sorry, it's not a question. You talk. Just a quick plug. Physics and astronomy majors, Friday, 2 to 3:30, 57A or B, whatever. Physics forum, please come.
There will be
I
snacks.
was waiting to announce that until, everyone was here. So, and not, yes, Friday. We will see you all there. Also, tomorrow we have round 2 of capstones, and there's pizza there as well. So I know that you guys as college students want free food, so please come to that as well. Janessa, is this for Emilito or for something else? What's your question? Let me bring the mic.
That's an exceptional question. What am I doing after I graduate? Well, I'm not quite sure right now. It's an interesting question. Yeah, just to be totally honest, I don't really have a clue. I'm actively searching for a job, yeah. Yes.
All right, let's give Emilito another round of applause.
Coming up next today is Caitlin Ohms. Caitlin has been working with Dr. Smith. And to preemptively answer Janessa's question, she told me that she has a position lined up at the National Space Intelligence Center after graduation in a couple weeks. So she doesn't get a summer break. All right, Caitlin, we good to go?
Hope so.
Excellent.
So hi everybody, my name is Caitlin Ohms. Just to preface this, I am still recovering from a cold, so if my voice maybe sounds a bit scratchy, I apologize in advance. But today I'm going to be presenting my research on the development and operation of a nitrogen Arcjet thruster. And so to start, just here's my amazing, wonderful team. We have a nice even split of both physics and engineering students. I really couldn't have done this without them, or our wonderful mentor, Dr. Smith, who is in the crowd right now. And so for the semester, we had 3 main goals: to optimize the Arcjet plume, to calibrate our LVDT, and to advance the construction on the thrust stand for our Arcjet. And so just a little bit of background on the Arcjet. An Arcjet is a specific type of electrothermal thruster. It works by heating up a propellant or gas through a method known as arcing, and then that propellant is then thrust out of the thruster from the nozzle at very high velocities, producing thrust. Arcjets specifically are really great for long-term and deep space missions, satellite repositioning, and like optimizing the payloads. And our specific Arcjet uses N2 as a propellant. We use a tungsten rod that serves as a cathode and a brass encasement that serves as an anode. Those two together produce arc, and it is all expelled outside of the brass nozzle. We are also working on measuring the thrust. What you're seeing on screen right now is a linear variable differential transformer, abbreviated to LVDT, and we have calibrated that by taking our own measurements of voltage, as it is a very sensitive, as it measures very sensitive changes in the position. And we are also working on constructing a thrust stand. We are aiming to get very small amounts of thrust in the range of a couple hundred micronewtons. So our thrust stand needs to be both precise and sensitive. To do that, it was designed following an inverted pendulum. And as you can see on the left, there is a CATIA drawing of the thrust stand. And so first to optimize our Arcjet, we originally noticed that it was having, that it was producing suboptimal plumes. And originally we thought that the reason behind this was that the tungsten rod was misaligned. However, as we continued testing, we found that it was actually our N2 propellant was escaping out of the front of the thruster, which is where our tungsten rod goes in, instead of the nozzle, which you can see in the picture. To remedy this, we got a rubber stopper and drilled a hole into it that snugly fits our tungsten rod, and by inserting that into the front of the thruster, we are effectively both stopping the N2 from exiting through the front, and we're also making sure that the tungsten rod is aligned in there so that it still produces the correct voltage readings. As you can see here, these are the before and after pictures of our measurements. On the left, though it is very pretty and colorful, there's hardly any plume being produced, which is a problem when you are testing a thruster. But then on the right, you can see that even though it's not as colorful, there is a more prominent plume. It is much longer and more defined, more powerful. Then to calibrate our LVDT, we took measurements of the change in voltage and also the change in the distance of the core within the coils of the LVDT. According to our manufacturer, this relationship between the voltage and the distance should be linear. Our results in our plot show that it is. And these results will later be used to do the testing of actually measuring the thrust. We'll be reading the voltage output and we'll be converting that to a distance. And for our thrust stand specifically, previously none of the parts had been fabricated for this part of the experiment. Until this year, we were actually able to take the drawings and the materials that we had and actually create most of the parts for the thrust stand, which are ready to go. One of the only things that is prohibiting us is currently, we did have a scaling error with one of the machine parts. It is, the water jet cut it to actually be 2 times larger than it was. Just would like to point out that all of our CAD drawings are scaled correctly and that it was in fact the fault of the water jet, as the machine shop let us know. However, that is a very easy fix, and once it does get fixed, the thrust stand will be ready to actually be built. Unfortunately, there just was not enough time to complete that this semester. And future goals for the project, we do want to finish building that thrust stand, as long as create a more secure and permanent way of plugging the propellant holes and securing that tungsten rod, as if we put too much gas in at once, the rubber stopper does pop out. We also, for the long term, would like to collaborate with other teams, and we want to finalize the testing process that will be used for our own Arcjet so we can maximize the amount of results we're getting. And we would potentially like to add a small servo to our Arcjet, as this would increase our efficiency greatly, because we can then remotely control the placement of the tungsten rod rather than doing it manually in the vacuum chamber. These are my wonderful sources. Thank you all for writing these papers for me to later find. And do we have any questions?
All right, we're going to take questions from students first.
Caitlin, do you feel like, since you had a mixture of physicists and engineers on your project, that reflects real-world projects and how they would do something like this?
I would say definitely. We definitely had like a mixture of ideas. A lot of the engineers maybe brought some things to the table that us physicists wouldn't necessarily think of, a lot of problem-solving solutions. But then we also brought some of our own physics knowledge when trying to solve various problems that we were having. Like, one of the problems we had was that we actually were receiving no voltage readings, and a lot of the engineers thought it was actually a trouble with our machinery, but then us physicists kind of went on and concluded, with the great help of Dr. Smith, that it was actually a problem with the tungsten rod being too close to the brass, and that was causing a shortage.
Chris. Randy, you have a question?
So what would be the benefit of these Arcjet thrusters over current Hall thrusters, which already have pretty good ISP and thrust?
These are pretty good, especially specifically for like nanosatellites themselves. Hall effect thrusters are really great, but this is just like another method of going about it, and the more that we research it, we can actually find out the capabilities and target which specific parts of space travel that they can be used for.
I guess my question, Whoever asked that question probably knows a lot more than me, but we've seen a lot of work on the alternative propulsion, and my question is, when are we going to see it in these big rockets that everyone's launching? Kind of naive question. I don't know what the status is, but just wondering like what's taking so long.
Yeah. So we're probably not going to see a lot of this used for big rockets for probably still a long while, just because as it stands currently, it is still, for the missions that we are trying to accomplish as far as using big rockets, it's just more efficient currently to use chemical propulsion. However, as electric propulsion becomes a bit more mainstream and it does become more powerful, we would hope to see a change in the future.
Let's thank Caitlin again. Oh.
Come tomorrow to the nuclear thermal propulsion talk that one of my students is going to be giving.
Shameless plug for another Dr. Smith student tomorrow. Got it. All right. Let's thank Caitlin again. Next up today, we have Demetris Ramirez. Demetris is going to be going to grad school at the University of Arizona to do some optics stuff to preemptively answer Janessa's question. And he's going to be talking to us about the on-source window for core collapse supernovae. Thank you, Demetris.
Perfect. So good afternoon. My name is Demetris Ramirez. For those of you that don't know me, I'm going to be talking about estimating the on-source window for core collapse supernovae. So just a brief overview about what I'm going to be talking about is what is a core collapse supernova and what is the on-source window, some similarities in supernova light curves, the quartic interpolation method, next steps, and acknowledgements. So what is core collapse supernova? Well, a core collapse supernova actually occurs at the end lifetime of a massive star. And so these massive stars actually begin their life cycle formed by hydrogen and produce fuel through nuclear fusion. And so as they go throughout the periodic table and they get to iron, it's actually the heaviest element that can be produced in this nuclear fusion. So when the core actually produces iron and exceeds in about 1.4 to 1.5 solar masses of it, it actually becomes unstable. And that basically means that the force of gravity becomes the more dominant force and collapses into the core, hence getting that core collapse supernova. So the reason that it's important is because the first phase of the core collapse supernova process actually contains all the details of the physics behind the supernova. However, it is not accessible to us with electromagnetic observations. We do believe, however, that it is possible to study it with the gravitational waves produced at this stage. And so that leads a little bit into what the on-source window is. And so this on-source window is basically the interval of time that we can say with the desired confidence that it contains that gravitational wave emission for an optical supernova target. This on-source window is actually made up of two different types of ingredients. The first one is actually estimating the time of shock breakout, and the second is estimating the delay between collapse and shock breakout itself. So we'll actually explore a little bit into that first one. So in a study that we've seen with different types of supernovas is we actually noticed that that first month of expansion shows a lot of homogeneous between different shapes of light curves that they have. As we can see in this picture, between that first month, they look pretty similar in that rise time itself. And so we ended up reading this paper about it and took with that to basically make a physical assumption that we believe that we can use a light curve that actually has a pre-shock breakout data and perform a polynomial interpolation to see if it estimates the time of shock breakout correctly. And so one thing that we also have to consider is we were looking at ground-based telescope data, and we only had data that had a pre-shock breakout that was something that was a space telescope. So for example, that Kepler data on the top is actually Kepler 2011A. And so because it is not a ground-based telescope, we had to basically make it to account that we have to alter it to be more of a ground-based telescope. And so when we're performing the polynomial interpolation, we started with a quadratic function. And if you guys can see to that bottom right, that the quadratic function actually was very biased, as the data collected days or hours or weeks after the time of shock breakout revealed that it actually had an observation days earlier than it should be. So we then moved on to the next physical interpolation, which was a quartic fit. And that quartic fit actually showed unbiased and was more reliable data set, as you can see, starting from that same data point that a quadratic would start and showing more towards that time of early observation. So again, talking about the Kepler data, we had to make sure that it scales to a ground-based telescope So we decided to basically sample 10 random data points between its first months of expansion and trying to model it similar to a ground-based telescope, such as Supernova 2019 EHK's results here. And so you can see above is the Kepler and below is the 2019 EHK, and they look pretty similar in those types of light curves. So when we were taking the Kepler data, now that we can perform that quartic interpolation method, we actually know the time of the shock breakout pre, so we were able to perform and see how well and effective this method was. And so we ended up performing a Monte Carlo method where we plotted different types of interpolations from 10 random points that were selected within the uncertainty of the Kepler data. And so for those of you that don't know Monte Carlo, it basically is used to predict the probability of various outcomes itself. And so by sampling 10,000 different samples, the reason we did 10,000 is because we started seeing consistency between the standard deviation and our histogram value. But after running that 10,000 samples, we actually got histograms produced as the figures shown. And so as you can see, that standard deviation actually contains within those different samples the time of shock breakout, which is at the 0 point itself. So now that we know basically a better understanding of estimating this time of shock breakout, we then can look into what is the relationship between this shock breakout and the collapse for the supernova. And so we actually looked into a paper by Couch et al. That talked about the relationship between shock breakout and ZAM's mass. And so if you had a progenitor whose mass was known, you could actually use this relationship with the Stern-Schneck model, those black data points, to determine the delay between the shock breakout itself. However, because if you don't know the mass of the progenitor, you can do a conservative approach where we use an upper limit of 17 solar masses, which corresponds to a 3-day delay that you would subtract from your data. And this is because of, in Smart et al., it talked about the red supergiant problem, which meant that any star that was over 17 solar masses actually was not really found in the local universe. So this is just a brief summary about the quartic interpolation, putting it into a diagram of terms. And some current and next steps. So the current steps, we actually are going to be publishing a paper that basically talks about us using this method on 3 supernova candidates that did not have a pre-shock breakout flux. We are also performing this method on other supernova candidates. For future, we want to also observe the difference between using magnitude light curve data or flux data, and then just looking into the effects of the known pre-shock breakout value. So other than that, I would like to thank Dr. Michaela Zanelin, my advisor, as well as some of my research fellows. I also want to thank Dr. Noel Richardson as well for helping us with the light curve data and using an interpolation. I also like to thank the rest of the physics department, my classmates, and my family for these 4 years. I've learned a lot at Embry-Riddle, and it's been fun. So other than that, lecture slide, and thank you.
What questions do we have for Dimitris? All right, Dr. Bailey.
I have a question. Can you go back to the original light curve slide? Yeah, this is fine. So you're fitting a light curve. You're trying to find a function that fits the light curve versus time. So A, has someone done that before? B, is there a theoretical model that would predict it?
Yeah, so to answer the first question, so when people are doing these type of interpolations to estimate the time of shock breakout, they're using a more of a physical model itself, where they're running physical simulations of what is the mass of the progenitor, what's the decay of nickel, and they're putting that into basically a pipeline that models it for them and determines it that way. However, we decided, what if we don't know like the decay of the nickel? What if we don't know the mass itself? And how can we interpolate it? And so that's why we decided to do the interpolation. And so from what I know, I think we are the only ones that are starting to do the interpolation method, because I know we've given a couple presentations to LIGO and they have not seen it before. So, yeah.
Last call for questions. Okay, let's move on. Let's thank Dimitris one more time. Next up, we have Mari Beltran, who's been working with myself on what is the driver for the luminous blue variables.
Okay. Hi, I'm Mari Beltran. Good afternoon. And for the last 2 years, I've been working with what's driving the variability of luminous blue variable stars. So starting with some background, luminous blue variable stars, or LBVs, are massive, bright stars. If we look at the HR diagram, we will find them towards the upper left. So these are the hot, really bright stars. They are also characterized by their high mass loss rates, which can be up to several solar masses. of material. When we're talking about variability, this is the change of brightness over time, and these time scales for these types of stars can be from days to centuries. The evolution, evolution component of these stars, like where they fit, has many theories, and one of the most accepted kind of theories that are being worked on is that they're a byproduct of binaries. So for this project, we had goals that we wanted to go through. We wanted to extract light curves from TESS, the Transiting Exoplanet Survey Satellite, and then take these light curves and perform and analyze Fourier transforms, and use the results of the fits of the transforms to look into the internal driving mechanisms. Up here we have an image of TESS, and then we also have a sample light curve, which is, as I said, brightness, so magnitude over time. So our light curves were extracted from TESS. TESS has high precision photometry, and then so we have these light curves. Because TESS does what we call, or what data dumps, it has to send information back to Earth. It will look at its target, turn back to Earth, and then go back to its target. So there are some error into that. So we need to make sure we have the correct magnitudes for this. So we used the ASSASSIN data, the All-Sky Automated Survey for Supernovae. It is a ground-based telescope that continuously watches the sky, or continuously takes data, and so we can find that reliant. So we fit the TESS data onto the ASSASSIN data. And then these light curves are what we put into period 04 for the Fourier analysis. So the Fourier analysis, this is the overall power distribution as a function of time scale. So this is how likely a power output would be for a frequency. On your left is the Fourier analysis for P Cygni done by Elliott et al. We used similar methods for this. And so for us, what we did was we did a chi-by-eye fitting the Fourier analysis, and then using those initial parameters into a limb fit, which is a curve fitting model, and then to more solidify these parameters and get errors for them. With the parameters, we'll be comparing, contrasting, looking for patterns, seeing what's consistent, what's not consistent, what's weird, what's not weird, and using those to look into the internal driving mechanisms. And then currently we're working on writing a paper for this, and Becca, my research partner, is looking into galactic LBVs and their spectra to further classify these stars. In conclusion, we used light curves from TESS to perform Fourier transforms so we can get parameters to characterize the internal driving mechanisms, and then using spectra to further classify the LBVs. Thank you.
What questions do we have for Mari today? All right, Randy has one.
So you said you were using ASSASSIN data to fill the blind spots of TESS, basically? Is that right?
More to, they're moving it. So I had the green lines for TESS. Those would either be way up, a higher magnitude than it actually would be. So it was more not to fill in the blind spots, but to overlay and show where it kind of should be.
Okay, so when you overlaid the data, the ASSASSIN data with the TESS data, did you have to do any extra corrections since it's a ground-based telescope?
No, I don't remember doing extra corrections for that.
The main thing Mari and Becca were trying to do with that was they were trying to make sure that the long-term trends of the light curve were kept, whereas
we don't necessarily have that with the short baseline of each little observing bit that you get with tests. Otherwise, you'd have to throw the long-term variability out, which is really what you need to understand the LBVs better. All right. Any other questions for Mari today? Okay. Let's thank her one more time. Next up, we have Caleb Colucci and Mitchell Novak. They are giving a joint presentation, so they'll have a little longer time to talk. And they've been working with Dr. Smith.
So I'm Caleb Colucci.
And I'm Dr. Sorry about that. I'm Mitchell.
Got ahead of himself. And we worked with Dr. Smith on characterizing the momentum distributions of muon decay products. So specifically, the muon decay we're looking at is up there at the top. So the muon decays into a positron, a electron neutrino, and an anti-muon neutrino. And there is the Feynman diagram for that decay. You will be seeing it a few more times. So to start, we needed to find the decay rate of the muon, and then we can find d gamma dp for whichever particle we are interested in, either 2, 3, or 4. This is Fermi's golden rule, and so right now we have everything there except for that matrix element with the goofy looking M. So our Lorentz invariant matrix is here. That's how we defined it. As you can see, there are 3 V's, which are anti-particle spinners, 1 U, which is a normal particle spinner, which from the Feynman diagram you can see is path 2 for the electron neutrino. That's the only particle that is normal. But going back to Fermi's golden rule, we need to square the matrix, so we multiply the matrix by its conjugate. And then we're able to use Casimir's trick, which is outlined there, because in the form previously, it's not very useful. Then Casimir's trick allows us to simplify this down to a product of traces, which are simply just the sum of the diagonal matrix elements. The P slash there is simply P times gamma mu. Then trace element identities allow us to simplify this even more. And then, if you don't believe us, this expands and simplifies down to just a product of momentums. And then the last step we have to take is just averaging over the spin states, simply dividing by 2. And then, as you can see by the Feynman diagram again, which paths relate to each other, so 1 and 2, and then 3 and 4.
Yeah, and then so we can then use this matrix element and plug it into Fermi's golden rule here and actually try and start to solve for each of the different momentum distributions. In general, what we want to do here is we want to try and integrate out whatever the other 2 momentums are that we aren't solving for. And so in this case that we're going to show here, we're going to be solving for the positron momentum, which is particle 4. So we're going to want to integrate out the 2 neutrino distributions, or neutrino momenta there, so P2 and P3. And so what order we do this in is fairly arbitrary. So we're just going to choose to integrate out P3 first. To make that easier, we rewrite the matrix element here in terms of just P2. And then, performing that integral, we end up, setting up that whole integral, we end up getting this. It's just expanding that delta function stuff, we end up getting just single one and then the delta 3 there. And that ends up being fairly easy to integrate. After doing that, we end up just getting this one up here, which is a little bit more annoying to integrate, but eventually we can do that down and just end up getting this here. Ends up integrating over all of the different angles and stuff for the P2 particle. And then, so then eventually this is almost our final form here. We just need to expand the D3P4 in terms of just the, just the absolute value of the momentum there. And doing so, we end up getting this. However, this is a little bit of an ugly equation And luckily, we can sort of simplify it quite a bit by just the fact that the mass of the muon is about 200 times the mass of the electron, meaning that it's pretty much just zero, so we can make that approximation and end up getting this pretty nice distribution here finally at the end. And then so finally, we can just quickly kind of, we do the other two. The steps for doing the other two are very similar, just kind of with a bit harder integrals and stuff. And yeah. Finally, we can sort of plot all of these to get a more visual representation of what's going on. And here we can actually see that the positron and the muon neutrino have the exact same, almost identical distributions here, shown by the blue curve. They end up both cutting off with a fairly hard cutoff there at around 50 MeV. For the case of the positron, actually, it in reality shouldn't cut off that hard. This is mostly just a bit of our calculations not being as precise as they could be. We could have done, or to fix that, we would have had to done some radiative corrections to it. However, that's a little bit outside the scope of this. The neutrino, on the other hand, would actually end up having a pretty hard cutoff there in reality, due to the fact that it doesn't actually have charge and will then not really radiate much stuff. As for the electron neutrino, you can see there, it actually does have a nice cutoff at the cutoff point there of half the mass of the muon. Yeah, thank you. Any questions?
Sorry, it's just a real simple question. How much of your capstone, I guess, did you spend doing derivations?
Almost all of it. Yeah, pretty much 100% of it, yeah.
Who else has questions?
Very impressed at the quantum field theory calculations.
Thank you.
What is the why did you have a 1/2 mu? Why does that show up? The dashed line there. What's special about that value?
Yeah. So from where was it? Was it that one? No, it was that one. When we end up when we evaluate the P2 integral, we end up getting the bounds that P2, or the momentum here, P4 actually, is always going to be less than half the mass of the muon there. So it ends up kind of giving us that big cutoff there. And we get a similar thing as well for the muon neutrino.
Any other questions for Mitchell and Caleb? Okay, let's thank them again. We have only one more talk today, but we have 7 more tomorrow. So everyone needs to come back tomorrow for more pizza and desserts, and obviously the amazing talks from our amazing seniors as they get ready to graduate from Embry-Riddle. Today's final talk is our own Clarissa Paveo, and she's going to be talking to you about a BE X-ray binary with a name that reads like a license plate, and some work that she's been doing with me the last couple of years. Take it away, Clarissa.
Thank you. So I'm Clarissa Paveo, and I've been working with Dr. Richardson on the properties and variability of the BE star CPD -292176, the descendant of an ultra-strip supernova. So some background on my project. What is a BE star? Well, it's just a massive star that I have depicted right there, and it's just a spectral type B star, and the little E next to it stands for the emission lines that it can show. And they are known to be rapidly rotating to the point of like critical rate where they would break up, and they also have this thing called a decretion disk. So it creates this disk of gas and dust around it just because it is spinning so fast. And when we first started this project, we saw an X-ray burst near the B star, and we wanted to see if they were in binary with each other. So that would make it a high mass X-ray binary. And high mass X-ray binaries are composed of a high mass component, in this case a B star, and an X-ray component, a neutron star. So we wanted to see if they were actually in binary with each other. So we used the CTIO 1.5 meter telescope in Chile, and we just got spectroscopic observations from there just to do our investigation. So the methods we used, like I said, there was that big disk around the star, and if it's a characteristic of a high mass X-ray binary to have the neutron star interact with that disk. So there'll be disk variability. And so we looked at a hydrogen line, just H beta to be specific. And on this plot here, if I can get here we go. There's like a weird trend in the data where it kind of has like that one peak and then it goes back down. And if I were to zoom in onto like the big, on the top right corner over there, that it would continue in a linear trend. There is variability within that disk, which does prove that there is some interaction going on with that neutron star and with the B star. But we weren't 100% sure that they were in binary, but that's a good indicator. And so we did confirm a spectroscopic orbit. So this plot here on the bottom is the orbital phase versus the radial velocity. And you can derive that from a helium line a prominent helium line from the B star. And so we were able to confirm that they are in binary with each other. But what made this project really novel and different was the evolutionary history. So we worked with a collaborator who's in New Zealand, and we gave her all of our parameters that we found, and she can put it through her system that fits to millions of different models of stars, binary systems that we know of, but it only fit to one. And we found this is only one system out of a handful in our entire galaxy, and the evolutionary history, so we were able to see the past of the star and the future of the star from this model. And so if we go through the steps together, stage one, it started off as two massive stars, probably two B stars. Then in step two, one of the stars got really big and started to heat up. It's ready to go end its life and become a supernova. Step three, it's now transferring its mass over to the other one. And then step four, it goes supernova. But in our case, it wasn't a regular supernova where it has this big explosion. It has something called an ultra-strip supernova. So this basically means it was just a really muted supernova. It didn't push away the other stars. So it maintained the binary system as well as maintaining an almost circular orbit. And most binary systems have a little bit of eccentricity, but this one does not really, which makes it very novel and interesting that it maintained that orbit and maintained a circular orbit while having a supernova. Now stage 5, that's where we are right now. That's what we're observing. That's the picture that was on the first slide. The B star with the neutron star. And then in a few million years, the B star will also go supernova, an ultra-strip supernova, become two neutron stars going around each other. Those two neutron stars will spin up really fast, and then it will produce a kilonova. And if we remember in 2017, with the big gravitational wave that we were detected, it would produce the same thing, but we will not be here to see it. So future work on this. I know this plot's kind of small, but it was just to demonstrate that we're doing a spectral atlas of our star versus multiple other BE X-ray binary systems. So ours is the red line, and then Tausco, is the blue line. We just want to see how it compares with other high mass X-ray binaries. And we wanted to just put all of our spectroscopic observations of that B star in a paper for people to reference, just to have a whole thing laid out for everyone. And that'll be published soon, hopefully. And that would be the conclusion of my senior thesis project, is getting that paper out. So, any questions?
All right, what questions do we have for Clarissa today? See, your talk was so good that there's no questions today. All right, before everyone gives her a second round of applause, I want to, Clarissa's still working on that. She's actively applying to places. That's the phrase we're using today. I want to also promote that we do have our annual department forum. Your chance to talk to all of your professors about what you like or don't like in the program as we work through things. That is Friday at 2 p.m. in Building 57B Friday at 2. So please come to that. And also come tomorrow to hear the remainder of the capstone presentations and have more pizza. So let's thank all of our speakers again. They did a great job. On behalf of the faculty in physics and astronomy, I want to thank all of our students for being so wonderful and doing this great work. It makes our job quite fun to do every day, and we look forward to hearing more of these tomorrow. So have a great day, everyone.